Okay, Namma. Correct on that. Hello. Hello. Good morning, dear students. Welcome to the fifth class on engineering mechanics for civil and mechanical engineering students. The principle of virtual work. Today we are mainly concentrating on the concept of the principle of virtual work. This is the part in whereas civil engineering students, it is a topic. It comes under statistics, but it is given at the end. We already covered system of forces, free body diagrams, equal beam equations, internal forces in structures, friction and its application. And this also now today we are covering the remaining are the dynamic part. Today we are mostly completing the kind that is the statics part. Whereas mechanical engineering students, this is what the virtual work. We have completed all these free body diagrams, equal beam, trusses, frames, and etc. These all are again dynamics part. Statics, this is one subject which we are considering today, the principle of virtual work. Now let us see what are the learning outcomes. What we are going to get from this. We can represent a virtual work and differentiate between external and internal virtual work. What is when we are applying a load on a body, there is some resisting force. Suppose if you consider a human body, I am putting 100 kg weight or 70 kg weight on your head. That is the applied load. That is the external load. Your body has some strength that will resist that force, and that the internal is force, the other one. See, these two virtual works you have to calculate. The virtual work, the differentiate between the external and internal virtual work. That is one thing. Then recognize and apply the concepts of state principles of virtual displacement and virtual forces. The principle of virtual displacement and virtual force. Based on these two, we have to calculate the virtual work. This is very, very important. We need a virtual displacement as well as we need a virtual forces. Force into displacement is a work done, as you know very well. Derive an expressions to calculate the displacement of structure using a unit load method. By considering a principle of superposition, suppose when all types of loads are acting, let us consider a system consists of concentrated load, moment, distributed load, distributed again, uniformly distributed load, linearly varying load, cubically varying load, quadratically varying load, etc. By considering one load at a time, you can, what is that load you have to calculate and apply a principle of superposition. You know very well the principle of superposition is valid for linear as well as non-linear. Virtual work can be applied for linear as well as non-linear. But here I already mentioned in the previous class, we are considering linear systems. So that's why non-linear part we are neglecting. Calculate the displacement or deflections of statically determined structures using unit load method. That means statically determined is the number of unknowns and number of equations, equal beam equation must and should satisfy. Because this is a principle we will apply for statics, that means we are assuming the system is in equilibrium. So that is one area where we can get the output. These concepts must really understood by the student. This is another method to solve the static problems and apply to the physical systems. Whenever you are dealing any problem in real life scenario, you have to apply this method, understood and apply the physicals. Updating knowledge of course as per the need of the subject. Sometimes depend upon the given data, you can apply your virtual work only. That you have to decide whether I have to apply graphical methods or analytical methods or virtual work concepts. Depend upon the data given in the problem. You have to update. That you have to decide. In the problem they don't give, you have to use the virtual work like that. Whichever is easy to based on the given data, that method you have to apply and get the solution very fast in a GATE or other competitive exams. See, these are the learning outcomes we are going to get after studying this principle of virtual concepts. Now let us see what is the introduction and definitions part. As compared with other methods like superposition, casting theorem, strain energy, if it is a deformable body. Virtual work method are the most direct method. It is a very simple method for calculating the displacements or deflections in statically determinate and indeterminate structures. Both is valid, but we are considering only statically determinate structures. Elaborately, we will discuss what is the difference in subsequent slides. What is the difference between statically determinate and statically indeterminate? Whether you consider beam or any structure, truss and other things. This principle can be applied to both linear and non-linear structures. That's what I already mentioned. But in our assumption, in the first case, we are considering a statically determinate structures and a linear system. The principle of virtual work is applied to deformable structures, is an extension of virtual work for rigid bodies. That is, not only rigid bodies, deformable bodies also, this principle can be applied. That's why we are considering internal forces as well as the external forces. Or in other words, this may be stated as, if a rigid body is in equilibrium under the action of system of forces, and if it is very, very important, please all of you listen very carefully. If a rigid body is in equilibrium under the action of a system of forces, and if it continues to remain in equilibrium, if the body gives a small displacement, virtual, like let us delta x, delta u, delta v, delta y, delta any virtual displacement, then the virtual work done by those force systems of forces, as it rides along these displacements, the virtual displacements is zero. That is, sum of the virtual force into virtual displacement is equal to zero. Sum of the force into virtual displacement. That is what we are calling as the virtual work. In the truss also we discussed, I hope if you recollect yesterday class, when the truss is in equilibrium, if you can consider method of joints or method of sections, in method of joints, the joint if you are considering separately, that is also must and should be in equilibrium. Similarly, in method of sections, if truss is in equilibrium, if you can consider sectional part, that is also must and should be in equilibrium. So this is how generally we will consider, if a rigid body is in equilibrium under the action of a system of forces and it continues to remain in equilibrium, if a body is given a small virtual displacement, that is the negligible displacement, then the work done by these forces and the virtual displacement must and should be zero. Along the virtual displacement must and should be zero, because system is in equilibrium. Instead of summation of forces 0, it is the multiplying the virtual displacement is equal to 0. That's all. That's what the virtual work. Many problems of structural analysis like bar, truss, plate, beam, etc. Beams, frames, shells, plates, etc. These can be solved by using the principle of virtual work. See, this is what is the concept which we are utilizing to solve static, linear, non-linear, statically determinant, and indeterminate, different types of problems. But our assumption is we are solving statically determinant problems and also linear systems as per this subject is concerned. Now let us come to the rigid structures. How the principle of work can be considered. Now later go to the internal forces. This is the virtual work is the total work done by the applied forces and the initial there is a initial forces, external force only of a mechanical system or a civil system as it moves through a set of virtual displacement. Applied force into virtual displacement. The force may be active force, reactive force, external forces. If it is a dynamics, convert into a static like inertia force, etc. Dynamic problem can be converted into static problem by applying inertia force in the opposite direction to keep in the equilibrium. That equilibrium we are calling the dynamic equilibrium, like D'Alembert's principle and other things. That we will see in the later when we are dealing with the dynamics part. When considering forces applied to a body in static equilibrium, the principle of least action requires the virtual work of these forces to be zero. The virtual work of these forces must and should be zero. Virtual work is the work done by the real forces acting to a virtual displacement or a virtual force acting to a real displacement. So this analogy is very again important. Real force acting through a virtual displacement or a virtual force acting through a real displacement. This is also vice versa condition is valid. A virtual displacement is any displacement consists with the constraints of the structure. If a roller is there, hinge joint is there, fixed support is there, the roller is sliding like that. So the hinge joint is rotation. Like such a displacement, any consists with the constraints like roller support, hinge support, fixed support of the structure that satisfy the boundary conditions at the support source. A virtual force is any system of forces in equilibrium. Then once again I am repeating, the virtual work is the work done by a real force acting through a virtual displacement or virtual force acting through a real displacement. Both ways you can represent the principle of this virtual work. Now let us consider mathematically how we will represent the same definition. It is one of the textbook, Megahill textbook, vector mechanics for engineers and statics. Imagine the small virtual displacement of particle when it is acted upon by several forces. A real force with virtual displacement. The corresponding, let us say, A is a particle, that is the position, and forces are resolved F1, F2, and F3, Fn. There are n number of forces. This delta R is the distance, that the vector length. The displacement, if you can resolve the vectors, F1 into delta R, F2 into dot product delta R, F3 dot product delta R. Because the delta R is a common, if you can separate. These system of forces have a resultant force R. That resultant force into delta R can be represented as the principle of the virtual. Imagine the small virtual displacement of a particle which is acted upon by several forces. When you want several forces are there, if it is better to find out the resultant force, multiply the virtual displacement. Or in other words, if a particle is in equilibrium, please see these analogies. If a particle, rigid body and a system. System means a mechanical or a civil system. Rigid body is one body. Particle is a negligible dimension. Consists of atoms, molecules, electrons, etc. If a particle is in equilibrium, the total virtual work of forces acting on the particle is zero for any virtual displacement. If a rigid body is in equilibrium, the total virtual work of external forces acting on a body is zero for any virtual displacement of the body. If a system of connected rigid bodies, the number of rigid bodies like IC engine mechanics, so we have beams, roller support, hinge support, fixed support and a beam. Like that, the system consists of number of rigid bodies remains connected during the virtual displacement. Only the work of the external forces need to be considered. That means, as for engineering mechanics problems, we will consider the total work of forces acting on a particle, the total work of external forces acting on a rigid body, the total forces acting on a system. We have to consider and find out the work. These are the three areas where we are using the principle of virtual work. This is very, very important when you are dealing a particle. Generally, these are the three cases we will come across. It can be a particle, it can be a rigid body, or it can be a system. In the real scenario, we will try to see these are the three types of problems. The system is any system. It can be a locomotive, or it can be an automobile, or it can be a aircraft. Structures, it can be a bridge, or it can be a tower, or it can be a frame, or it can be a truss, it can be a beam, bar, frame, like that any structures, shell, vessels, etc. So these are the areas where we will apply the principle of virtual work. This is the real force into virtual displacement. The same in other way, the same thing here, but with respect to particle, the three analogies. Here what is the difference is, small difference. If you can see the first one, if a particle is in equilibrium under the action of number of forces, the total work done, virtual work, by all the forces of virtual displacement is zero. Force into virtual displacement. In principle 2, a particle is in equilibrium under the action of system of forces. If the total work done by the forces is zero for any virtual displacement of a particle. Once again I am repeating, if a particle is in equilibrium under the action of, earlier is the number of forces, here the system of forces. It can be concurrent, collinear, coplanar, parallel, etc. Earlier particle means one, anything you should act on that point only. That's why that case is different. That is also one type, but you don't get number of alternatives. This is the difference between the principle 1 and principle 2. The remaining part is same. Work done by the virtual work, total work done or virtual work done by the forces is zero for any virtual displacement. The remaining part is same. Third principle. A particle is in equilibrium under the action of system of forces. If the total work, the D is extra printed, the total work done by the forces is zero. For the kinematically admissible virtual displacement of a particle, don't violate the concept. Kinematically admissible means we are assuming that the system is conservative, there is no loss or no gain. Suppose if you are considering a piston cylinder mechanism, it is we are assuming conservative system. There is no losses. That's what kinematically admissible. It has to satisfy all equations. That is what is the meaning of kinematically admissible condition, virtual displacement of the particle. Don't violate the other conditions, other constraints basically. So these are the three small differences between the principle 1, principle 2 and principle 3. Sometimes in a particle also we are acting a system of forces. But there we can consider the point because work done, force requires three parameters. One is the magnitude, direction and point of application. To calculate the work done, the point of application is very, very important. Force into virtual displacement, from that point only we have to calculate. So that is the reason why, but only the difference is first case number of forces, here system of forces. Any type of forces you can consider on a particle only. But particle generally compare with rigid body and compare with system. Here system of forces combinations of few combinations are given. That's what I said earlier. Now let us see a simple analogy, simple mathematical representation. Virtual work is an imaginary work done, I am assuming, because you are giving a virtual displacement into real force, or virtual force into real, like that. When a particle is subjected to a number of forces, is moved a small imaginary distance. Mostly we will consider the imaginary distance virtual displacement only delta U. Here if you can see the system, I have given a free-body diagram directly. It consists of two external forces F1 and F2, or let us say it is a frictional force, it is applied force, weight mg, and then reaction M. Actually these two are weight acting downwards, normal reaction is upwards. But let us I assume these are the directions, the given diagram is given. N is equal to mg, one equation. N is equal to M. Vertical reaction. Because there is no work done perpendicular to this. Only work done is along this virtual displacement. There is no displacement in this direction. That's why sum of the force 0. Or otherwise this into positive, this into negative work done. If you can make it, that also is equal to 0. That also will give you an intensity. Or suppose if F1 and F2, or I add all the forces, this component, why there is no displacement in this direction? Because this is having 0 degrees, 0 work done. Or in other words, from here to here 90 degrees, from here to here 90 degrees. Those are all the components. That's why F1 into cos 0 into displacement, because 0 degrees. I am taking this as a reference towards right, whereas towards left, this is origin. If you can consider, this angle is 180. That's why F2 into du cos 180. Whereas these two components, the angle is 90 degrees. That's why mg into du cos 90, n into du cos 90. Then depend upon these values, you may get the positive and the negative. Finally, if you can resolve, F1 is equal to F. See the same equilibrium equation. Some other force in x direction 0. That also will give the same equation. Cos 0 is 1, cos 180 is 1, cos 90 is 0, and that's why the mg is 0, n is 0. That is what is the meaning. There is no virtual work done along the surface due to the gravity force or due to the normal reaction. That's because of cos 90 0 mathematically. That's why sometimes instead of representing every time those components, you try to neglect. That is the real system. Or this force, if I can apply in some inclined direction, which is making an angle theta, virtual. This force into virtual displacement along this direction. This is the displacement. If I want to calculate the delta d, this delta d cos theta is in this direction. The force into displacement. This is what the work. Theta is dependent upon the angle you have to substitute. If it is a vertically downwards, suppose force is applied in this direction. Theta is 90 degrees. You like that? If suppose I am using this constant in other direction, I am using displacement in the vertical wall, sliding down. See, this is how the virtual work is generally calculated for a rigid body. Here I have given a rigid body. Earlier I represented with a particle, now it is a rigid body. Now let us see the beam problem. Here is a system. The particle is analyzed, rigid body is analyzed, now a system, civil structures. It consists of two supports. Particles are system of forces, either particles are a system of or systems at equilibrium. Here we find out their reaction because see, the displacement is given on the right hand side. One is a hinge support, the other is a roller support. Roller support is having the vertical reaction only. Hinge support is only rotation, that would, or vice versa, you can change. Now if you can give a small displacement at this point, du, in this direction. So that's why work done is equal to summation of the forces. This is one force and this is another force. Remember, this is the reference point I am considering. That's why RA into, there is no virtual work of this, it is fixed I am assuming. Three forces, 1, 2, 3. This has a reference, this is 0 degrees. Cos 0 is 1. If we can resolve the angle, sin 0, whatever it may be. Here, as far as this force, what is the distance? If it, at RB length is L, at F, what is the length? See the length, if we can know the A value, what is the force? We can count or take a moment about this. RB into L is equal to F into A. From that, this is the equation. Some other moments. So now once we know this, apply this equation. This is RB in terms of F represented. RA into 0, because this is I am taking reference, this is the virtual displacement. F into A by L, this is RB. F into this force into A by L, because at this distance, as per linear ladder, this similar triangle, for L du displacement, for A the displacement. That's why A by L, F into A by L du cos 180. That component we are resolving. RB, because this is the displacement and this is acting opposite. That's why angle is 180. Whereas this displacement is RB du cos 90. If we can calculate the total displacement, one is positive, these two are opposite direction and these two are in the same direction. This is how generally we will try to consider the virtual work of a particular system, any system, if you can consider. Now let us see the rigid body subjected with three forces: F1, F2, F3, M1, M2 and M3. This rigid body is subjected with three forces and three moments. F1 delta 1, F2 delta 2 and F3 delta 3 and F4 delta 4. M1 delta theta 1, M2 delta theta 2, M3 delta theta 3 and M1 delta theta 1. There is force as well as moments. Okay? Because moment is an angular displacement, force is a linear displacement. But if you take a virtual displacement, it's delta theta 1, delta theta 2, delta theta 3, delta theta 4. Same earlier also, if you want to write instead of delta, you can write delta x1, delta x2, delta x3, like that. You calculate the total work. What I want to say from this slide is, the degree of freedom can be a translation or it can be rotation. Or sometimes I have said it is a combination of translation and rotation. See, because of that, what we are considering is, it will apply both translations and rotation degree of freedom. When you are considering such a situation, what we have to do is, we have to calculate the work done due to all types of degrees of freedom. Okay. Now sometimes internal forces, if you are considering due to internal force, it can be a bar or it can be a truss axial force, bar and truss axial forces. Beam consists of bending moment and shear force. Torsion consists of, again in terms of shear or torque. Here M is a bending moment, T is a torque. Calculate the strain energy, the resilience, energy stored up to static elastic point, half sigma into epsilon. Sigma is load by area. Epsilon is you can use the stress strain relations and represent the equation in form of this. and the boundary conditions you can substitute. Let us length of the structure is L, 0 to L. It can be a bar, it can be a truss, it can be beam, or it can be shell, or any type of structure you can consider. The strain energy. This is the energy generally will represent in terms of job. This is what are the internal forces, if you can consider, to resist external forces. Those forces are due to the deformations, or what we will, because stress and strain, it will come under deformation. Because we are considering up to the elastic point, we are not considering up to the plasticity. The reason is, in elastic point, if we can remove the load, it regain its original shape. Whereas in the plastic, it is not like that. It won't regain. That's in that case we are not considering. If remove the load, it regain its original shape. Okay? So that's why we are considering the strain energy for virtual work done. If it is a translation, it is half sigma into theta. If it is a rotation, instead of sigma versus epsilon, tau versus gamma, shear stress versus shear strain, because the torsion. In a rotation, there is half tau into gamma. That you can convert the strain energy in terms of like this. See, that's why degree of freedom can be a translation, can be a rotation, or can be a translation in terms of along the axis or perpendicular to the axis, shear, or again bending rotation due to moment. So these are the things generally we come across as per the internal event force of concern in system. This is also called as the strain energy, because we have to calculate the work done, and that is how we consider. Now this is what I mentioned. If you want to differentiate between the statically determinate and statically indeterminate structure. Till now what I explained is number of conditions of equilibrium which are available. Suppose if it is a two-dimensional problem, planar system, we have three equilibrium equations: sigma fx 0, sigma fy 0, moment 0. Whereas in case of 6 degrees of freedom space, we have 6 equations: sigma fx 0, sigma fy 0, sigma fz 0, moment about x-axis 0, moment about y-axis 0, moment about z-axis. In any system, whether it is a planar system or whether it is a spatial or a three-dimensional system, if in a two-dimensional planar system, 3 equations, in a space or a three-dimensional system, we have 6 equations. If these combination of equations are sufficient to solve your problem, that system is called the statically determinate system. If these equations are not sufficient to solve unknowns, that equation is called statically indeterminate. In that case, you have to consider some other equation, like compatibility equation, displacement equation, other things. See, that's what, if you can differentiate here, if you can compare, the conditions of equilibrium are sufficient to analyze the structure. If the conditions are insufficient to analyze the structure, that is the indeterminacy. If suppose let us take a simply supported beam, one end roller, another end hinge. Apply external load is applied. Hinge is only the rotation, something like this. Roller is something like, if I can consider, this is the roller. Rotation as well as translation. Unknown is vertical reaction. Hinge is only the rotation, the two translations, x and y. See, because of that, the total number of unknowns at joint A, 3. It's 2 unknowns, RA and RB. At joint B, only RB. 3 unknowns, we know the 3 equations: sigma fx 0, fy 0, moment 0. This is how generally we consider the system. And we try to obtain the equilibrium equations. Bending moment and shear force is independent of material and cross section area. Whereas in case of statically determined, bending moment and shear force is dependent upon, in the statically determined is independent, here dependent. Material and independent of the cross section. Material is independent and independent of the cross section. No stress are caused due to the temperature change and lack of heat, whereas here stress are caused due to the temperature change and lack of heat. Whereas the last condition is extra conditions like compatibility of displacements are not required to analyze the structure. Here extra condition like compatibility of displacements are required to analyze the structure along with the equilibrium equation. This is the difference between the statically determined structure. This is not only in this case, everywhere it is the same concept. We'll try to apply to differentiate between the statically determined structure and statically indeterminate structure. Okay. Now let us consider the analogy how we will adapt. In structures analysis, we solved many types of problems. Let us consider a simply beam. This is a beam. Consists of force and displacement F. There are a number of forces F1, F2, Fn. Apply principle of superposition. Consider the effect of this force. Due to this force, what is the displacement here? What is the displacement here? What is the displacement here? What is the displacement here, etc. Due to this force, consider again all displacement. Due to this force, consider like that you repeat. Now sum up. At this point, if I need principle of superposition, what is the displacement of F1? What is the displacement of F2, F3, Fn? You have to add all those because we are assuming linear and superposition principle. That's right. This is the actual system of force. But we are considering a virtual displacement, virtual forces vice versa. And this is the enjoint and it is a roller joint. Vertical reaction, horizontal reaction, vertical reaction. Three unknown, three equations. These are statically determined structures. That's what the analogy apply described here, which is an equilibrium under the action of forces F1 to Fn respectively. Let U be the displacements. The internal stresses is sigma stress strain. You will get half sigma into epsilon. Strain energy stored into dV. This is the inside on the beam. But it's subjected to second system that subjected to virtual like forces in equilibrium as shown. The second system of forces called virtual, as the imaginary are not part of the real one. These produces a displacement configuration delta U1, delta U2, delta U3. See, that's why the first this combination, then external force F due to the displacement, internal stress due to the work done, sigma epsilon. Or if it is a triangle, half base into height. Suppose stress strain curve, if you up to the elastic point, it is a linear, it is a triangle. The area of triangle is half sigma into epsilon. The energy stored in the summation of that we have to consider here, both external as well as internal. This is what since the beam is an equilibrium, the external work done must be equal to the internal work done. Hence, one needs to consider both internal as well as external work done to establish the equations of equilibrium when it is in a deformable nature. It is a deformable body. But we are assuming a rigid body. In that case, the other part which we are not considering. But let us, if I can consider that part, virtual displacement. This is what? A deformable body is an equilibrium. If the total external virtual work done by the system of true forces moving through the corresponding virtual displacement of the system is equal to the total number of internal virtual work for any kinematically admissible virtual displacements. I already explained what is the kinematically admissible. This can be represented as Fi into delta I. If it is a number of discrete, if it is a continuous system, sigma, because in the stress strain we are applying load continuously. That's why integral of sigma into epsilon. Whereas external we are applying loads at some point. That is sum of the effect of all the loads. And you have to integrate the internal stress. If you equate these two, this is what is called the, you will also can consider principle of virtual work for a deformable bodies. This is how generally we will consider the deformable body. Now, virtual forces. This is the virtual displacement. Okay, if I can give virtual displacement, this is the equation. If it is a virtual force, vice versa condition, you can see. Real displacement, virtual force. The earlier one is virtual displacement, real force. These are the external, these are the internal. Engineering mechanics will consider this pattern. In strength of material, we have to equate mechanics of materials. That is the difference between the rigid body mechanics and the deformable body mechanics. What is the virtual displacement? But as far as our syllabus is concerned, this we are assuming 0. We are assuming that even if it is deformable, we are assuming the structure is rigid, and we are giving a small virtual displacement. See, the system is in equilibrium or not. That's what we are studying. Okay. So now here the virtual force, total complementary work done. Earlier work done, now it is a complementary work because this is the real displacement, this is a virtual force. That work is called complementary work, is equal to the total internal complementary work of system, virtual force and stresses. Virtual force and delta, virtual stress. Multiply with the real displacement, real strain. Strain is nothing but in terms of displacement. The main, as I stated earlier, the principle of virtual work is advantageously used to calculate displacement of structures. Later, we will see how to calculate the displacement in a beams and frames, plus by calculating a method by using the virtual work concepts. Now let us see here the work done. We have to find out, but what I said is this is the force into displacement. If it is a triangle, half base into height. If it is a stress strain diagram, half base into height. Similarly, I am representing a force F1, F2, and U is the displacement. But let us consider the forces, external forces, may be in the form of a concentrated load, axial force, or bending moment, or shear force, M into d theta rotation, shear force, translation. If I can consider all those, but if you take instead of displacement like this, I am considering virtual displacements. This is the linear displacement delta, d delta. The virtual displacement due to rotation, the moment, rotation, and shear force. This one, translation in a perpendicular to the axis. This is parallel to the axis and it is perpendicular to the axis. Okay, that's why there are two translations and one rotation. Now it is the external work done. If you can see, the internal work done is strain energy stored in the system. Half sigma into epsilon that can be converted in this form. Sigma is load by area. Strain is change in length by original length. That if you can change in length, sigma is equal to E times epsilon is equal to sigma by E. Sigma again P by A. Then we get the P square by 2EA. Okay. Similarly, bending moment. Similarly, shear force. So this is how we will consider. Now consider the second system of forces, delta F1, that is complementary, delta F1, delta F2, delta F1, and displacement, which is virtual, causing virtual displacements. Let the virtual stress results caused by virtual forces of cross section of beam, and both are here, virtual force and virtual. That means you can take virtual displacement, real force, real displacement, virtual force, or both combination. because if you can change a small value, there is no much effect on the system. This is the third case. In the third case, apply the first system of forces of the beam, delta F1, delta F2, delta F3, system of virtual forces. Then the principle of superposition, we add it and obtain the result. So these are the external forces and these are the internal strain energy stored in the system due to the external force, concentrated load, a moment or a shear. This is how generally we try to represent the equations. Now let us consider cantilever beam. Earlier simply supported beam we have considered. Here only difference is this is due to the force and displacement. This is the virtual force, virtual displacement. And sometimes you will take combined system like this by combination of this plus this. F1 plus delta F1 is equal to U1, F2 plus delta U2, and F plus delta U plus delta U. This is how generally we will try to consider the actual system with the combined system. Now if we can calculate the total energy by kinematically eligible conserved system, we could write the combine all from J is equal to 1 to M. If you can combine, find out the expressions, and this is the general representation. But later we will see, apply some problems, we will come to the conclusion how it will affect the system. Now let us consider the problems now. Some simple problems. Here is a piston and cylinder mechanism. If you can see here, this is the piston. Firing takes place. This is a mechanical system. I am considering both mechanical because mechanical students are there, electrical engineering, civil engineering is also there. That's why I am considering both types of problems. Now let us consider. Almost we have done the introduction part is almost completed. Now let us see another remaining. We have another 1 hour time, more than 1 hour time. We will try to concentrate some of the problems. First, a mechanical engineering problem, a piston and cylinder mechanism. This is the piston moving in this direction, translation degree of freedom. This is the connecting rod, one end translation, the other end rotation. Why? Because this is the crankshaft is rotating 0 to 360 degrees. Okay. At some range, like coupler, it is oscillating. When moving forward, backward, this coupler is making oscillation. There is a like this. Or a pure rotation, 0 to 360 degrees. Now let us consider the virtual work done by the external forces. External forces P and firing a fuel. That is also external force. These two are the external forces I represented. And this is the crankshaft, the pin joint, and this is the moving normal reaction. Surface depend upon the roughness. Frictional force is there, but here we are neglecting. Now we have a hinge joint, two reactions, Rx, Ry. This is something like a translating now. This is a pin, but here it is a vertical reaction. That's what we are considering. We external forces, active forces, reactive forces. We are not considering any internal forces. Why? Because it is a rigid body concept. If it is a deformable body concept, that also we have considered. Okay. Now we have to consider the total work done. Here work done due to only because these are the constraints. Now the external, I have drawn a free body diagram by removing all surroundings, all constraints. I represented the system. Okay. Now once we know the displacement, calculate what is the delta displacement, the virtual displacement. Here the external forces are P having this displacement in y direction. Q is having displacement in x direction. That's why we need x component and y component. This component is having only x coordinate, no y coordinate. Y is 0. So that's why x coordinate is here. If you can see the problem, L is given, theta is given. Represented like this means if let us assume that it is known quantity, otherwise represent in terms of theta as a variable. I need x coordinate from here to here. L cos theta, L cos theta. Here vertical displacement from here to here. Because here we need a vertical displacement. This is L sin theta. Total horizontal is 2L cos theta. L cos theta, L cos theta. So that's what I have given. From here to here, this is the origin. From here to here, it is xp. That is L cos theta up to this, and another L cos theta. 2L cos theta. This x. If this is theta, this is 90 minus theta. Now this component L cos theta is in vertical direction, sin theta is in horizontal direction. That's why 2L sin theta. This is also 2L sin theta. Cos theta is vertical component. Because this L cos theta from here to here, only one cos theta, L cos theta only. Either this or this, both are same. But in horizontal, L sin theta, 2L sin theta. If this is theta, with respect to horizontal theta, then it is 2L cos theta, it is L theta. Like that we can vary. Now I need a virtual displacement because x displacement delta x. I am differentiating. This is a variable, theta is a variable. As you go on changing, theta is changing. Okay, xb 2L sin theta becomes cos theta into d theta. Similarly, yc, this one, L sin theta. This one is L cos theta. L cos theta is equal to delta y minus L sin theta. Cos theta becomes minus sin theta into d theta. Now substitute dxv d here. Now this is the equation what we get. U is equal to half p into tan theta. That is what is the force which is required. Q in terms of P. If the virtual displacement is consistent with the constraint imposed by supports and connections, only the work of load, applied forces and frictional force need to be considered. If the friction is also considered due to the constraints imposed by the supports. Okay. So this is a simple problem, a mechanical engineering problem. Now let us consider the civil engineering problem. A truss type of, there is a frame structure or a truss structure or any structure, and spring is also connected at the base. This is what is the spring, and this is L and this is L. Similarly, earlier problem, but it is not arising in mechanical. It is a structure, civil engineering problems. Determine the expression for theta and for the tension in the spring, which correspond to the equilibrium position of the spring. In unstructured positions, the spring displacement, the spring is having a HA length and the spring constant is K. Neglect the weight of the mechanism compared with the forces and the internal strength numbers. Now we apply the principle of virtual load. Draw the free body diagram first. If you draw the free body diagram, you apply load P here. These are the hinge joint two reactions because rotation, because it is a planar system. We have 3 degrees of freedom. Out of 3, rotation is possible. This translation is not possible, this translation. That's why AX, AY. Similarly, as far as this is concerned, this roller, rotation as well as translation in this direction. Now, unknown is vertical direction. That we are certain. F is a force. A and P. AX, AY are the forces and the joints. Now external load is P. Here I am considering delta U is equal to delta UB plus delta UF. Delta UB is this point, F, because spring force. 2 forces are acting. The vertical displacement here, the vertical displacement here. Both are acting in the y directional, the displacement, if you can see. Earlier one is x direction, the other is y direction. But here both the displacements are in the particular direction. But only difference is this point is having, this is L, this is L. This is L cos theta, either this or this. Whereas this one is 2L sin theta. 2L sin theta by C, B is L sin theta. See, this is how we will try to, because both are same. Earlier we got cos theta sin theta. Why? Because x displacement and y displacement. But here we will consider the x displacement in one direction and y displacement in the other direction. Okay. See now, this virtual displacement you have to count delta yb, differentiate L sin theta becomes cos theta into delta theta, delta yc 2L cos theta into delta theta, and spring force is equal to spring stiffness, that is Newton per meter, into length Newton. That's why K into delta or K into S. This S distance is, this is the S. If H is known to you, Y total length is known to you, then Y minus H, that is what we call the S. This Y H length is, you know, just now used. H is YC is total 2L sin theta. H is a variable at this particular point because of what is the spring force level, S or X is unknown. H I am keeping. See now, force into displacement. This force into this displacement. This force into this displacement. And the F is equal to Ks, you substitute K into S. Now we simplify, neglect higher terms. Higher term is delta theta square, like that. Those terms if we can neglect, are throughout divided by delta theta. That is also another way. So now simplify, you will get the sin theta expressions in this form. From this, we can get F is equal to half of the spring, that is the force. Now let us see a pendulum. That is a compound pendulum basically, not a simple pendulum. What is the principle which we are adapting here to get the displacement? Okay. If a mechanical system, this can be a mechanical system or it can be a compound pendulum, because connecting rod is a compound pendulum. Any cross-sectional member, any member, human being, if we can hold like this, also a pendulum. Any system. With some independent generalized coordinates, Qi, K is equal to 1 to N, is in static equilibrium. Then the generalized force associated with these displacement must be 0. There is independent generalized coordinates, static equilibrium. Some of the forces can be determined. If a system is having n degree of freedom, then n independent generalized coordinates are required to specify the system, because number of independent coordinates are required to specify the degree of freedom. That is what we are in. Independent coordinates required to completely define the configuration. Hence, for n degree of freedom system in equilibrium, we can write n independent equations. Okay. For a simple pendulum or a compound pendulum, we can calculate the torque required to hold the bar in some angle theta using the principle of virtual work. The force due to theta direction or force due to some other parameter to find out equal to 0. So this is what is called the work done, or a force, or a moment. Weight is equal to mg. Weight is equal to mg. This is the value. This is the displacement. This is L by 2 cos. L by 2 cos theta is vertical. L by 2 sin theta is horizontal. Okay. That's what we can resolve the component mg downwards. The x component and y component, you find out ith vector and jth vector. From here to here, L by 2. Sometimes you can use vector notation also, not only scalar notation. Rotation is about z axis, m, theta. M into k, because both are in the same direction, like z axis rotation. But here translation is in x and y. When the body in translation takes place, x component, here see, x component is L by 2 sin theta, y component is L by 2 cos theta. At one location, another location, like that. You have to consider the equation. From this, whatever the unknown, you have to find out. So this is how the energy can be calculated. This you differentiate. I've given here the expression of F, how it is represented. Okay. Now let us consider another problem. This is again a civil engineering problem. Calculate the relation between active forces P and Q. This is one active force P and this is one active force Q. For equal beam of system of forces, one end is fixed, that is A, and these are the lengths L and L, like that. If you can consider, if L is the length of each side of the bar, theta is the angle of made by the each side of the bar, theta. Then distance P takes place from here to here. That's why you sum up the total displacement. Q consists of P displacement is in this direction, Q displacement is in this direction. See, because of that, what is happening is, this point with reference to this, we have a displacement only this length only. Okay. So this is how we'll consider a problem. Especially buildings, cleaning, etc. We will use this type of system. Similar system will consider mechanical also, or structures application. Okay. So now theta is a variable now. This shape can be changing. Structure is rigid, but the shape can be changed. Theta value can be changed. This length is L cos theta, 2L cos theta. Here also 2L cos theta, 2L cos theta, 2L cos theta. Total 2L, 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 8L cos theta. Virtual displacement. Similarly, Q, only L cos theta, L cos theta, 2L cos theta. See, these are the virtual displacements for force P and force Q. So this is how we will calculate the virtual displacement. Here, in principal virtual problems, you have to be careful about calculating the virtual, that is the virtual displacement. Forces are anyway active forces. Displacements, you have to consider the virtual displacement. How to represent the virtual displacement depend upon the, because force and displacement should be in the same direction. P along P only displacement you have to consider, not in along any other direction. So that's why P into the virtual displacement at point B, Q into the virtual displacement at point C. Okay. Up to that, with same reference point, calculate the what is the displacement. Because this is the origin reference point. From this Q, this is the displacement. From this only calculate P also. This point should not change. The reference point should not change. See, that's why from here to here, if this is theta, this is also theta horizontal, this is also theta, this is also theta. L Sin theta is this, L cos theta is this. This is again L sin theta, L cos. Total horizontal, because displacement is in this direction, not in this direction. That's why 2L cos theta, 2L, 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 8L cos theta for this P, and for this Q, only 2L cos theta. See, that is how we will consider the displacement. Now calculate let the vertical displacement P is B dash, B moves to B dash, A moves to A dash. That is the vertical displacement. 6L cos theta dx, x is equal to 6L, 8L cos theta. Now dx is equal to 8L into cos theta becomes minus sin theta into d theta. Similarly, dx2, L 2L sin theta, 2L cos theta, this one, 2L cos theta, 8L cos theta. This is L cos theta, L cos theta. This is 2L cos theta, 2L, 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 8L cos theta. Now, the total, the displacement in with reference to Q force, dx2 minus 2L sin theta. Okay. So now we have to calculate. One is positive. This is 8L. Some of the force work done is 0. P into dx1 is equal to Q into dx. Both are in opposite direction. Now substitute dx1 here, dx2 here. Minus 6L sin 8L actually it is 2L. Now simplify. It is actually 8, not 6. 8. 8L, find out the value. Now go to the second problem. A prismatic bar AB, a ladder it is. Note down otherwise. A prismatic bar AB of length L, total length L, and weight Q, stands in a vertical plane and supported by smooth surfaces, that is frictionless. Smooth means no friction. Smooth surface at A and at point A and point B. Using principle of virtual work, find the magnitude of horizontal force P applied at A if the bar is in equilibrium. If the bar is in equilibrium. If you can consider the problem, see this is AB. This is the initial displacement. Or virtual displacement, either how we are using the displacement. One is initial position, the other is displaced position. This is generalized case I have considered. A moved to A1, B moved to B dash, or A moved to A dash, B moved to B dash. This displacement is x direction, initially x and y. X is from here, L cos theta, y is L sin theta. With reference to this point, it is different. L by 2 cos theta and L by 2 sin theta. Okay. That is how we will consider the x displacement is this, y is only L by 2 sin theta. Now if you can consider that, this is the equation C. X is equal to L cos theta and y is equal to L by 2 sin theta. Let the horizontal P from D is x is equal to L cos theta. Then dx, virtual displacement is cos theta becomes minus sin theta, d theta minus L. Similarly, the vertical displacement y is L2 sin theta. The virtual displacement is L by 2 cos theta d theta. Okay. The normal reactions at 2 points, Ra and Rb, have no work along the planes. Now substitute force into displacement, P into this and Q into this. If we equate, that is x. P into dx is equal to Q into dy. One is a clockwise, another is counterclockwise. Here substitute this L sin theta d theta dx dy L by 2 cos theta d theta. From this we can get P is equal to Q by 2. This sin theta, if you move other d theta will be cancelled. Q by 2 into cos theta. See, this is one of the values, other can be determined. See, this is how the problems can be solved for different systems. Okay. Now go to the third problem. This is a truss problem, basically. But here what I have given problem is find the axial force, S, this is S, in the bar of the simple force by using method of virtual law. Only I want to determine this force. No need of all other force. Because there is no displacement here, in joint, it is fixed. Only it is a rotation. Only the displacement takes place only this part. So initially EFDB can be moving B dash S like this, the shape. Okay. So this is how generally we can consider this displacement is moving B to B dash, the virtual displacement. This is the height H, this is L by 2 and this is L by 2. This is the in joint only 2 reactions, roller joint only 1 vertical reaction. Okay. Let S be the compressive force. I am assuming it is a compressive. These arrows you can follow compressive like this or tension opposite or vice versa. That is your choice. But that is one type of representation. Let S be the compressive force in bar CD. Consider the EBDF. EBDF of the given diagram. Applied force RB. This is RB. This S and P. These are the forces. Active forces, internal forces, and reactive force. The 3 forces we are considering. Active, external force, reactive, internal force, yes. Okay. Now, in a rigid body, we will try to neglect this. There is no, we are not considering any force of internal impulse. But if it is there, keeping fixed and giving EB as the angular displacement, this one, EB becomes EB dash. This is center. Now D moving to S, this location. B moving to B dash. Okay. Angular displacement is D alpha. Guess what? Now from this, you see the triangle. This is D alpha. Originally EBF moved to B dash and F dash. Okay. Now, if I can take moment about this point, because method of sections, if you apply, I am applying only this force into perpendicular distance into this force into perpendicular distance. By using considering external system, find out the reactions first. RA and RB. Accordingly, we will get RB value. Now, see RB into BB dash is L by 2 D alpha. BB dash This is L by 2, cos d alpha and sin d alpha. Small virtual displacement. That cos alpha d alpha you are considering at the end. So this is what d alpha. L by 2 d alpha, a bb dash, ff dash is equal to h d alpha. This is the h. Okay, the virtual displacement. And the component, and the component is equal to rb into L by 2 d alpha, s into h d alpha. If you can find out, s can be represented like this. Now, if you can consider the whole frame is in equilibrium, bidirection. External force, internal force. External force is Ra, Rb. Okay. This is how we will consider the external force, Ra and Rb. This is the internal active external force, and these are the reactive forces. This is the internal force. So now this is Ra vertical reactive force Ra, and this is Rb. Okay, Ra plus Rb is equal to external force P. That's what we have considered here. Ra plus Rb is equal to external force, because here two unknowns, Ra and Rb. Then take moment equation. Moment is about this point or about this point. Here Ra with respect to this point, Rb into total L, P into L by 2. This is counterclockwise and this is the clockwise. So this is what Rb into L. Now two equations, two unknowns. From this, L will be cancelled, Rb is equal to P by 2. Similarly, Ra is also equal to, one still is P by 2. Obviously, other is also P by 2. Then substituting these equations in the first one, Rb is equal to P by 2, P by 4 into L by. So this is how we will consider the different problems. And now this is another problem. If you want, you can do it at home. Now let us come to the some more problems. Now let us consider this problem. This is what I given a first problem. Is example like this. To clean these are vertically represented, sometimes with wall house, like one sliding member is created. In that the bar is slide. This problem we can be consider here, which are composed of interconnected members like this, can move relative to each other. Various equilibrium configurations are possible. Method of virtual work is suitable for this type of problem when there is a pin connection like this. Okay, the concept of work done by a force and stability of the systems we can determine by considering the principle of virtual work concepts. Now let us consider some more systems. When we are considering work done by, this is already explained, but the force is acting earlier parallel, now it is inclined like this. Okay. This F is F cos alpha and F sin alpha. If the force and displacement is along this direction, we resolve the force. If I want to keep force as it is, displacement can be resolved. This is ds cos alpha. Okay. That is how we can work done by a component of force with this virtual displacement or vice versa conditions can be considered like this. U is equal to F cos alpha into ds, or U is equal to F into delta S alpha. But if you can see, both will give the same result. F ds cos alpha, F ds cos alpha. The choice is yours. Okay. See, instead of force considering in this direction, let us consider force in the other direction, like this. But moving in this direction. One is a push and another is pulling. Okay. See, in this case, what is happening is it is angle theta. This is f cos theta. F cos theta into ds. Okay. But here, this force and direction both are acting in opposite. So definitely we get the negative sign. Force and displacement opposite direction. Here force and displacement are in the same direction. See, that also you have to calculate when you are calculating the work done. Okay, these are some more analogies I am adding for to solve the virtual problems. See, this is what a vector notation. Yeah, most of the earlier case we have done a scalar notation. If you are considering a vector notation, work done by the force, this one. In this case, generalized force is acting on a particle, the displacement is A into AR. This is the dr. Both not in the same direction. Now what we have to do, this force has to resolve in the x direction, y direction and z direction. That's what d is equal to f along the surface ds. dr is equal to, dr can be resolved along ds cos alpha and ds sin alpha, like that. This component, dr is equal to this component, this component. This is ds cos alpha along the force and this is ds sin alpha. This is ds sin alpha. You know that because this force is dr cos alpha. See, that is how we will write along x component ifx, ify, jf, kfy, kfz into idx, jdy, k. The dot product. From this you find out this is the expression. Or in other words, f into dr, resultant force will be g, nothing but fx, dx, fy, dy, fz, dy. The generalized case is dx and ds. dx and ds. ds is surface. We represent as cos alpha and that can be represented here. Here if we can consider the pulley, this is again a pulley is moving pulley, the fixed pulley, two blocks are sliding, or a pin subjected with two forces. These problems, forces which do not work, force applied at the fixed point, forces acting on a done normal to the displacement. I already mentioned. Along the displacement, force will give a work done, this don't give work done. Reaction at the frictionless spin due to rotation of a body around the pin. No actual work. Reaction at a frictionless surface due to motion of a body along the surface. No work done. Weight of a body with CG moving horizontally. Weight is acting downwards. This weight cannot do work done in the horizontal direction. Similarly, normal force is acting in vertical direction. This cannot do any work done. Why? Because cos 0 is, cos alpha is 0. Reaction and friction due to rotation body, we are neglecting that. Reaction at a frictionless surface due to motion of body along the surface. Weight of a body along the surface or horizontally. Friction force on a wheel moving without slipping. See, these are the cases where we will consider forces which don't have any work done. Some of the work done by several forces may be zero. Body is connected by a frictionless pin, like this. Body connected by inextensible cord, like this. Internal force holding together parts of rigid body. Internal force, this one. Work done by sometimes a couple. See, this is the equal and opposite force are acting here. Equal and opposite force. The force is forming as a couple. Moment is equal to force into distance into angular displacement. Okay, so that is what is m into d. If it is a counterclockwise, assume positive, clockwise, assume as negative. The total work done can be calculated by the integration of from limits. You apply the boundary condition, try to solve the problem. See, this is how generally we'll try to represent the concept of the virtual work. Sometimes the rotation, that is, the force is not in the form of a force, it is in the form of a couple. When you are applying a couple, what is the work done? The energy stored in the system. Dimensions are generally, it is nothing but, will count as joules, there is nothing but Newton meter. Work done by force of 1 Newton moving to a distance of 1 meter. That one. Dimensions of work of a force and moment of a force are same through their entirely different physical quantities. Work is a scalar quantity, given a dot product involves product of force and distance, both measured along the same way. Moment is a vector quantity, given a cross product. When is a vectors. That is dependent upon your convenience. As for notation is concerned, you can use a scalar notation or you can use a vector notation. Okay, some textbooks in engineering mechanics, my dear students, most of times some textbooks they will use scalar notation like Timoshenko angle, whereas Beer and Johnson and Hibbler, James, these are the textbooks where you use the vector notation. Singer, Timoshenko Yang, these are the books where we use the scalar notation. Whichever is convenient, you can follow with that. That is not a big problem. Scalar notation or vector notation. So now let us consider a problem of virtual displacement is not experienced but only assumed to exist so that various possible equilibrium positions compared to determine the correct one. Imagine a small virtual displacement delta R. This is the delta R, which is acted upon by several spring forces. S1, S2, S3, S4. The corresponding virtual work is this F1. This is a free body diagram. Delta R is the displacement. This is F1, F2, F4, F3. This F1 component along delta R, F2 component along delta R, F3 component along delta R, and F4. Like that, if you can add on up to n number of participants there, we can find out the what is the total work done. Okay, so this is another way we can represent same problem in a vector notation. Earlier it is a scalar notation, and now it is a vector notation. F1 delta R, F2 delta R, F3 delta R, and F. Expressing in something a vector notation, I Fx, J Fy, K Fz. Now I delta x, J delta y, K delta z. Now if you can consider that if dot product I dot I is 1, J dot J is 1, by using that you find out this is the line. Then the sum is 0, you can get 0. This condition of 0 virtual work for equilibrium is both necessary and sufficient, since we can apply it to the three mutually perpendicular directions, three conditions of equilibrium: Fx 0, Fy 0, Hz 0. Okay. The particle is in equilibrium. This is already explained. The total work done by due to virtual displacement also it should be in equilibrium. The work done of all external forces acting on a body should be 0 for a virtual displacement. Since work done by internal forces equal, opposite, collinear cancels with each other, that don't contribute. This force system cannot contribute any work done. That's what the okay. Collinear forces. Now consider the in this aspect some more similar problems are tried, but this is the one type of plane. Let us say ABC. This is B distance, A distance. This is the horizontal of B. This is a fixed frictional spin joint, fixed. Only rotation, translation. The roller joint, translation, rotation in this direction is possible about axis. This is not possible. Okay, that's why I am using unknown here. Or I am making a vertical displacement delta. Okay, work done by this force and work done by this force. That is P into A delta theta is equal to work done by R into B into delta theta. Okay, one is a clockwise and another is counterclockwise about this point. That's why we are using from this equilibrium moment equation. This is what is PA is equal to RB or P is equal to RB by A or R is equal to PA by B. See, this is how the virtual work can be determined. This problem I already earlier explained. Same problem, piston and cylinder mechanics. This is already solved. This also I already solved, but only extra added here is this is a piston again, sliding. Okay, P is acting here, F is acting here. One is a vertical pole, another is spring is connected earlier. But now I used it is a translation and it is a rotation, it is a connection. Similarly, I see in mechanism, but I applied P and F. The active forces work done. This is the reactive forces at this point and this point, and these are the internal forces like tensile and compressive. Okay. In general, we will consider if you real system, we will consider three types of work done due to the external forces, due to the reactive forces here and here, due to the internal forces like member is a tensile or compressive. Accordingly, we find out, consider the what is the total work done. Major advantage of the principle of virtual gravity, it is not necessary to dismember the system in order to establish the relation between the active forces. Active forces are determined directly without reference to the reactive forces. The method is particularly useful in determining the position of equilibrium body of system under known loads, because it is a rigid body concept. These advantages are there. The method requires the internal frictional forces do negligible work during any virtual displacement. If internal friction is appreciable, like rough surface, smooth surface will neglect. If it is a rough surface, work done by internal frictional force must be included in the analysis. That's why, depend upon the type of problem. If it is a reformable body, we have to consider the internal forces, not only reactive and external forces. See, like that, depend upon the system, you have to consider what type of and again, this is very, very important, the degrees of freedom of the system. Example of 1 degree of freedom here, like 4-bar mechanism, IC engine mechanism, this is also 4-bar, sealing, crankshaft, connecting our piston. This is fixed and this is fixed. 1, 2, 3, fixed link, 4. Any of this we can consider. See, this is one coordinate. Two coordinates are here. Translations and rotation. This pulley, rotation as well as translation. This is also rotation and translation. Whereas here, not like that. See, this is how generally we will consider the system with number of degrees of 2, 3, 4, 5, 6, 7 like that. Let us take an example system with a friction. It is a sliding friction or a rolling friction. I already mentioned this point. The friction can be a sliding friction or friction can be a rolling friction. During virtual displacement delta x and this is delta theta. Okay. And here the tangential force mu kinetic friction by n, impending motion. Here the sliding friction, here the rolling friction. This is the static friction and this is a kinetic friction. Mu k into n into dx. because gravity is acting downwards, and this is horizontal, P into delta x. Delta x is the force and the frictional force is F. F is in terms of normal reaction. Normal reaction is mg. That's why mu into mg. Mg mu mg. That is what we will consider the total work done. Not only that, you can calculate the efficiency also. Okay, output by input. Some system is getting energy here for the virtue output work is necessary to elevate the block mg cos theta. The efficiency of the inclined plane is this mg cos theta. Input work is T into delta S. This one. If you can equate, we'll get this relation. Okay. Now, stability part we are not. Now let us consider similar problem we have done, but here only one bar here. The difference only thing is translation as well as rotation is constant compared with the previous problem. Translation and rotation. This is due to P and due to M. M delta theta, P delta XD. XD theta. Okay. Delta theta along positive, theta increases with delta theta. M delta theta will the same sense. X will be, if it is C, rotation, X will be decreased. This is an X. If it is in this direction, it is increasing. Now, if this XD is equal to L, this vertical component. Okay, this is L, and this is L. From here to here, it is 3L. L cos theta, L cos theta, L cos, 3L cos theta. Delta x, the differentiate both sides, 3L cos theta becomes sin theta. Then M delta theta is moment into delta theta is equal to this force into total delta L. Delta L is this. Force into moment. If you can simplify, finally you will get like this. This problem I already we have discussed. Same thing. This problem already, the repetition. So now let us consider here the work of a force corresponding to displacement torque at any angle ds cos alpha. If it is a positive, both are same positive. If both are opposite direction negative, like depend upon what angles we are in. Alpha 0, alpha pi, or alpha is equal to 90 degrees. Okay, the three cases at any alpha. Along work done 180 degrees, opposite negative work done 90 degrees. Block resting on a plane surface, perpendicular direction, no work done. That's what this is the case. Okay. Work of a couple, this is already explained. The work done by a couple. F into dr1, F into dr dx to find out the value. Work done. Then this is also already explained. This also explained. This also explained. I will consider some more cases here. Let us consider this problem is already given, and now consider this one. A generic observation for rotation of a rigid body where this is the rigid body concept BA. With respect to this is sliding like this. Okay. Now this is what is AB, BP. This is AB. This is AP. This if it is L, L cos theta, L sin theta. Okay. Delta, this is the x component and this is the y component. Delta x is delta sin theta, delta if L delta, if I can assume as a delta, then differentiate. This is vertical and this is horizontal. That's what is the representation. Wherever it is coming, you have to differentiate that. The similar problem. Assuming frictionless contacts, determine the magnitude of P if it is an equilibrium. Similar problem we have done. Ladder problems. Here see. This is the displacement. I am representing only the diametric representation. Earlier I have not shown this. A is moving to, this is the xy displacement, this is the x displacement. This is a translation. Originally, this is the case. Now L sin theta d theta, L cos theta d theta. If you can use the expression. Now let us, this is the new problem. The pressure P driving a piston of diameter 100 mm is 1 Newton per mm square as the configuration is shown. What weight W will the system held in a frictionless is neglected. The pressure P, this is the pressure P driving a piston. But in addition to that is the load lifting upwards, downwards. Okay. This is 100 mm diameter. At the configuration shown, what weight W will be the system hold if friction is neglected. This is the problem. Okay. Initial is A, B, C. That is with little bit handmade picture we have considered here. A, B, C. Move to delta x displacement. A1, B1, C1. And from here to positive, and from here to negative. C dash, B dash, A dash. Then the total displacement C is equal to delta x1, delta x2, this one and this one, or delta yb, y1. Find out the C moment. Okay, the total the ladder moment, because vertical is always same everywhere. Horizontal only there is a variation. Only I am representing the analogy. Now the remaining equation we can get the similar to the earlier. Okay. Now let us consider the hydraulic lift platform. It is a lift for loading a truck. It will slide like this, and it will when it is vertical it will slide, and then it can translate. Keep this box inside the cabin or inside the aircraft, anything. Okay. If the data is given, hydraulic platform for loading truck supports weight of 5000 Newton only. One side of the system has been shown, the other side is identical. Then here, if the diameter of the piston of the cylinder is 40 mm, because if I need a force pressure into area, I have to multiply. For that, some of these dimensions are given. Now you can see, this is what. After making a small displacement, it is combining these three displacements are like this. Okay. So that is, if it is the value of 2 theta, this one. Okay. The 2L cos theta, this is the L value. This is L. L along this. L cos theta, and this is L cos theta, and this is L sin theta. Like that, you can count the value and obtain the what is the delta theta as well as the translation part. Okay. Now this is another problem where hydraulic landing gear type truck or a truck similar truck with it will lift this box will push into the aircraft. Okay, the data is given in the problem, and this can be represented as the similar. What is the virtual displacement from the geometry? But from the gate point of view, you don't get this type of complicated problems. Now, this is also another problem where we can consider the force P applied to slider C as shown. The constant of spring constant is K is equal to 1.6 kilonewton per meter, and the spring is unstretched when a member BD is horizontal. Neglecting the friction between the slider, this is the slider, and the guide rod, this is the guide rod. Knowing that BC is equal to BD, determine the magnitude of P so that when the system is in equilibrium. This is what you can consider the P-body diagram. This is the Q, this is the P. Okay. Initially CBD, that is the initial diagram. This is L and this is L. In this bar 300 mm, it is 2L. When it is moving D to D dash, B moving to B dash, and this is fixed pin, and this displacement C is moving to C dash is Q, and here I am using a frictional force is P. Okay. Now find out this is the delta x1, delta x2, and that is what tan theta from the geometry. This is tan theta, tan phi, and delta this is x2, the x1 is this from the geometry. Now the principle of virtual work done is Q into this displacement, P into this displacement. Okay, both are in the same direction, positive or negative. What sign convention here is it? Here into delta x1 is already we got, delta x2 is already we got. Okay, then is equal to 0 because virtual work done. Then Q is equal to this by this. This can be, if you want, you can further simplify. Okay. Like when you are using a cutting plier, I am applying, I am holding like this, the top force and the bottom force. I am applying here, top and bottom. Okay. So this is the block. Resting. This problem can be solved, represented like this. Okay. The diagrams, this point, if you can see from the geometry, here this is the mechanism. B point, D point, this is one lever, BD. Okay. OD is the another point. There are two levers. Okay. This is R. ODR. And similarly, we can consider when it is displacing D to D dash, making an handle. This is the handle part, and this is the jaw part. Okay. This is also a displacement here, C delta theta. Okay. From that geometry, find out what are the angles, horizontal component, vertical component from the geometry. Similarly, vertical distance and here, and find the equations. Okay. See, this is how we try to get the equations, but in the gate point of view, this much cumbersome problems don't get. Okay. Now let us consider this is another simple problem where this is a fixed pulley, this is also a fixed pulley, and this is the block. Determine the equilibrium for system shown. The pulleys are frictionless and having a masses W1, W2 and W3, the three weights. Now if we can represent this, the force, this is another problem where a member is having the force Q and here the two forces are applied. Okay. This is the X displacement, these two are Y displacement. This is another type of problem, similar geometry. Then here, this is the translation, this is the rotation, and here mass is attached at the other end. This is also a similar problems can be solved by using now if we can see here the same problem from the geometry. This is the initial position 1, 2, T1, this point, this, and this is the mass. When it is displaying in this direction, this is moving to this point, this is moving to this point, and this is also moving to here. Okay. See, like this, if you can consider the points, the displacement taking place here at point A, at point B, and at point C. From the geometry, this is equal to L. This if it is L, this is also L, and this is also L. At the center of gravity, L by 2 cos theta and L by 2 sin theta. If you can use the three displacements at each and every location, find out the forces, corresponding forces into the displacements. You can get the moment and find out the total value. And this is again a truss problem where you have a hinge joint reactions. These are the reactive forces and these are the active forces. If a member consists of deformable body, you have to consider the internal force also. By considering these forces, these are the internal forces. If you can remove this member, there are two forces are acting. Weight is given or external force. Find out the work done. Okay, similar problem we have solved earlier. Please try this at home. Simple logic C. Here delta C is the actual displacement, delta D we have determined, and delta E. Here also actually, when it is moving from C to C dash, D to D dash, E is moving to E dash, find out the virtual displacements and determine whatever the unknown you can find out. That is FCD into the virtual displacement at C, and this component to virtual displacement and this component to find out the unknown value. This is already done, but only extra thing what we have added is here the forces, some more loads are applied, P, 2P and Q. Okay, there are three forces, but here earlier we applied only horizontal forces. Now we have applied vertical forces. Earlier we have applied Q here, P here, and this is not roller support. Now one end is hinge and another end is roller, and two forces are applied, P and 2P and Q. And this is X direction, this is X direction, these are the active forces and these are the reactive forces. With this we can determine a similar problem, but earlier only considered X direction, now we have to consider the Y and other direction. This is another problem where we can consider to lift the body upwards, downwards, like heavy weights. Okay, and where the members are, this is something like a piston and cylinder. These are the pin joints freely moving up and down. This is the total weight. Okay, when it is going upwards, these will expand. This component is having rotation and this component is having a translation. So like this we can consider the number of types of problems. Today with this I will stop my lecture. See, today we have completed all static conditions. Tomorrow we will consider the dynamic nature. If you have any questions, please send the Google Forms. We will try to give a reply. Please clarify your doubts. And once again I am repeating, in a static problems, today what we have discussed are how to apply principle of virtual work by considering a real force virtual displacement or virtual force real displacement or a combination of both, vice versa conditions. That is one aspect we have discussed. Then unit displacement method, how to adapt for civil engineering structures as well as mechanical engineering systems. Any system, even electronic, electrical, same thing is valid. That is one thing. We have considered particle, we have considered rigid body, as well as we have considered system also. Okay, different systems are considered and try to analyze how to apply the principle of virtual work. See, that means what I want to conclude is we can solve the problem with graphical method, we can solve the problem with analytical method, we can solve the problem with trigonometry, and this is another method, the principle of virtual work. See, the choice depends upon the data given in the problem, we have to select which method we are going to use. So these are the topics we have covered in the statics part for different systems. From tomorrow onwards, we will go to the dynamics part, the remaining classes I try to spend on dynamics. Please send your queries or any clarification, even a small ambiguity, Google form. Immediately we will try to give a reply. This material available with the organizers. Please get from them the YouTube, the video audio as well as the PowerPoint presentations are available with the JNTU team. They are very happy to conduct these guided classes with in collaboration with JNTU, Anantapur, JNTU, Kakinada, Yogananda University and Dr. B.R. Ambedkar. Thank you very much for giving this opportunity. Have a nice day, my dear students. Thank you very much.